Today, Megan Korchinski and I are going to talk about rifting from collapsed origins to passive margins. And we're specifically going to address the question of what factors lead to rifting or not, using 2D numerical models of extension of continental lithosphere. And we take a parametric approach in which we evaluate some initial parameters and then track them through the models. For example, we start with initial crustal thickness of 60 kilometers, talk about that very briefly, and then in more detail, 40 kilometers. We'll, in many cases, look at deep crust viscosity in weak, intermediate, and strong cases. And we'll also look at the effective extension rate. So the initial rate of extension of pulling on the lithosphere from either side of the 2D model, either fast or slow. We'll also evaluate the effect of sedimentation. And in cases in which we allow sedimentation to occur in the basins that form, we'll look at low density sediments and compare those to high density basin infills, such as would happen in the case of mafic volcanic material. There are many other parameters that go into these models and all the details are in a couple of papers by Korchinski et al. I just talked about what the key parameters are, and this slide is just to give you a visualization of what the different layers look like of the system. So shallow crust, deep crust, lithospheric mantle, and asthenosphere. You'll see these colors throughout the model outputs. Once the extension starts and the model starts to develop, you'll see in some cases melt in various regions of the model, and we'll be able to quantify melt fraction and also strain rate. You'll see regions of high strain. So very briefly, just the parameter approach is quite powerful, we believe, and you can see through time, either in movies or in snapshots, we'll look at both, how the different parameters affect the system as it evolves. And you can look at feedbacks, both positive and negative, and other interactions of different parts of this system. So not to overwhelm you, but this is just showing some of the features that we'll be looking at, and we'll pick out a few of the key ones and demonstrate those in more detail to you. So just very briefly, the orogenic crust, if it collapses either without sediment in the basin or another end member is with dense basin infill, in all cases of orogenic crust collapse, we see deep crustal flow, typically on fairly dramatic magnitude, both laterally and vertically, though more so with the weak deep crust. And the key feature here is the decoupling of the deep crust and the mantle lithosphere, which does not allow lithospheric rupture to occur. So even if we ran these models out for many more millions of years than what we're showing here, we would not see rifting in the sense of rift to drift transition. We think it's useful to look at this end member case before we go to the thinner crust examples, because we're seeing here how the crust can thin. For example, starting with 60-kilometer thick crust, in not very much time, we have crust that's nearly half that thickness. And this may be a very important stage in setting up the lithosphere for what can happen later if extension either continues or occurs at a later time, because we've also cooled and stabilized the crust through the vertical deep crustal flow to shallow levels. And so even though rupture doesn't occur here, we have thinned the crust. And now Megan will talk in more detail about what happens to 40-kilometer thick crust under lithospheric extension.
Okay, so I'm showing a couple of movies here about the 40-kilometer fast extension with a weak deep crust, and you can see that even at 3 million years, we have formation of lithosphere penetrating shear zones. These are going to start this localization of deformation. We still have quite a wide rift right now in the upper panel, and then eventually it localizes into the center, into what we would consider a nascent oceanic basin. If we add some dense basin infill into this model, it's a fairly similar result. We do see some really interesting competition between vertical uplift and subsidence of the basin. But at the end of this model, you can see that we're localizing our extension on the left-hand side, right above that blob of melt in the asthenosphere. The next slide is going to show you some screenshots where we're varying the viscosity of the deep crust. So you can see even at 2 million years in the strain rate that we have a really well-localized high strain high strain zone in the center of the model where these lithosphere penetrating shear zones are, and then we go to drifting pretty quickly because the lithospheric mantle and the entire lithosphere is very strongly coupled. The intermediate deep crust, it's a little bit less localized because there is some flow of the deep crust that's taking up some of this extension. And then when you get to the weak deep crust, there's quite a bit of high strain in the deep crust, which is showing this flow of the deep crust. Okay, so let's focus in on the strain rate here. I'm showing this high strain zone in the upper panel, and then the flow of the deep crust in the lower panel. And I do just want to highlight right now what's happening in the intermediate deep crust, which is kind of a combination of the two things happening. And this is a really interesting result that's come out of the models that we're focusing in right now. So if we look at the timing between this happening, I'm going to focus on 3 different stages in the models. 1, the formation of the shear zones, 2, the rupture of the mantle lithosphere, and 3, the rupture of the crust. And if we look at the timing, which I'm showing here in this bar chart, you can see that it's fairly what you would expect. There is something, one of the things that we were not expecting is this late rupture of the mantle lithosphere in the intermediate deep crust, which you see, it's not as easy to see in the fast models, but when we get to the slow 40 kilometers, it's really quite striking. Okay, we're going to look at another model video here. This is slow extension with a weak deep crust. And what happens here is now the model's at 11, 13 million years. You can see we still haven't started to form these shear zones. Instead, we're having homogeneous thinning of the lithosphere. The shear zones are starting to form now, and we go from formation of the shear zones to the localization of deformation in the center at a nascent rift at around, I've got the times here. So the strong, intermediate, and weak, we start with the strong on top, and you can see at 30 million years, the shear zones are well developed in both the strong and the weak. Are developed in the weak, not well developed. But however, in the intermediate deep crust, it's not until quite a bit later that they start to develop. I have the times for us in the next one, but let's look at the shear zones here. This is showing you the development. In this, you can really see this. These wide occurrence of faulting that happens in the 10 million years. So now let's focus in on these strain zones and the timing. The high strain zone in the intermediate deep crust, which is our center panel, forms at 35 million years. This is 5 million years after the weak deep crust and 9 million years after the strong deep crust. What we think is happening here is you have, in effect, a competition between localization of deformation along the high strain zones and flow of the deep crust. And this competition results in delay instead of being additive. It's delaying, basically. Both of these deformations want to take up space. So let's add some, let's look at this bar chart again, sorry. So here we have, again, 3 different stages, and you can see here really well this dot, which shows the formation of the shear zones is much later. Again, the rupture of the mantle lithosphere is later, and in actuality, the model doesn't go to drifting because we stopped them at around 40 million years. Okay, let's add some low density basin infill here. The timing of these processes, this is the experiment output. If I look at the strain rate on the next slide, the timing and the localization of these processes, the timing of these processes is not as striking as the difference between the slow and the fast. But the way that the deformation localizes horizontally across the model, so like laterally from the outside in, is very different. This seems to be the main impact that the sedimentation has. Is it's not so much, when we were first looking at it, we were looking at these changes in timing. It's not so much it's changes in timing, it's the changes in where the deformation localizes. So the big one here, the easy one to see, is the intermediate deep crust, which is now only localized in the center. If I add a high density basin with a weak deep crust, we are seeing again that there is this competition between subsidence of the basin and uplift of the weak deep crust. This is our fast model. So we did basin infill on all of the experiments, and it's actually something we're focusing in on right now, is to really understand how the sediment changes this localization of deformation across the model. Okay, and finally, this is our summary of the ones that we've shown here. The last signal I want to talk about is that the timing that we see here in phase 2 in the slow experiment suite in the lower panel is very similar to what is in effect phase 2 in the FAST experiment suites. In the FAST experiment suites, we go from phase 1 to phase 2 within the first couple of million years. We don't see this long phase, but then the timing from the initiation of phase 2 to rifting is very similar between the FAST and the slow experiment. This was quite unexpected because the slow experiment is pulling by half, and yet they seem to go at the same time speed, over the same time scale. We were exploring this more, probably to do with what Donna was saying about the thinning that has occurred previous to the formation of these lithosphere penetrating shear zones. Even though it's pulling slower, it still goes roughly the same order of magnitude towards drifting.
Okay, so just to start to wrap up, showing our parameter space here and some of the things that we're tracking visually as well as quantitatively, we can see some fundamental differences in 40-kilometer thick crust between fast extension and slow extension, in particular how they behave with the different parameters that we've explored. So a few key points that Megan has mentioned have to do with the coupling or decoupling of the lithospheric layers and how those affect the timing of rift to drift. And we've evaluated these largely by how we varied the deep crust viscosity. And in the fast extension case, you saw that there was rapid failure of the lithosphere and because of the strong coupling with strong crust. And then with weak crust, we saw development of a wide rift because the crust stretches so much, and we see a delay in lithospheric rupture. And sedimentation, in this case, under fast extension, was only important if the basin infill was dense, like in mafic volcanic materials. For slow extension, we saw quite interesting behavior depending on, related to the slow extension, where the first phase, it looked a lot like the fast extension with more uniform extension controlled by the strength of the lithospheric mantle, and then transition to phase 2, where we have significant rifting and drifting over 12 to 15 million years. And we touched on this a bit. Megan talked about the interesting features that we saw for intermediate deep crust and how there are different feedbacks, positive or negative, for the different cases of different deep crust viscosities. So thank you for listening to our talk. Today, Megan Korchinski and I are going to talk about...
It was too long. So there's time for a couple of questions. If you have one, please type them in the chat or just write Q if you have one. Maybe Suzanne, I think you had a question. Do you want to start? Oops.
Sure. I can still see your playlist, Sasha.
Oh, okay, yeah, I work on that.
Thanks. These are interesting models, amazing model suite that you've run. I was wondering a bit about your initial condition. When I understood it right from looking at the figures, you have this inclined weak zone that goes through the entire crust, right? So I find it first of all fascinating that it seems that on a crustal level, it doesn't seem to introduce much asymmetry, even though it's an inclined weak zone, but it does at the level of the lithospheric mantle. And my other question related to this is, what was your motivation for choosing this as, I know you have to choose something to start the models off with, right? But what was your motivation to choose an inclined zone like that?
This may be a Donna question. Donna and Christian and Patrice did quite a bit of testing on a single zone of localization, or on one side or on the other. And we decided on that one because we wanted, it was in effect a ratio we were comparing across them. So as long as it was the same through all of the parameter space. But there, and I wasn't here, so just, Donna, you can chime in, but they did do, they tested a weak, like just a seed. And then Donna, I think you tested both left dipping and right dipping.
That's right. Yeah, it doesn't really matter as long as you put it in the same place each time.
Now that's interesting, because we've been comparing different ways to start our rift models off as well. More like one seed, several seeds, numerical noise, inclined, the whole bunch. And it often does matter in a way, because it sets your initial failure patterns. And these then play into the next stages. So it's a resolution thing partly.
Or I guess it's maybe it depends on what your definition of matters or doesn't matter is too, right? I mean, like the first order, the processes that we saw didn't matter, but you're right in terms of some of the asymmetries that develop. In that sense, there may be an effect.
Yeah, because it develops some asymmetry at the level of the mantle lithosphere from what I saw from some of the models where Megan was stepping through in more detail.
That's right. That's right.
Yeah. Anyway, thanks a lot.
I'd have a question on what you modeled as slow rifts, because there's a large spectrum of rifts that are much slower than 1 centimeter per year. If I think of East Africa, and the entire East Africa would be a slow rift, and there are some with 1 millimeter, 2 millimeters per year. Did you explore this really slow, ultra slow end members, and how much change would that bring to your models?
No, and I would really, really like to. We put it down to 1 because we wanted to half it and not change the order of magnitude of the rifting and see what happened when it's a little bit slower, but not too much slower. And that would be an obvious next step would be to go to ultra slow. I've got to do the thing that I learned about the parameter space is you get too much information almost. So it was kind of going through the first 2 and finding these signals, and then we would go to the next big change like that. But that would be a definite an area to explore.
Okay, thanks. Last question from Roger.
Oh shoot, I don't know.
There we go. I was just wondering about how weak the faults are, and I was thinking also about some recent models that Luc Lavier has done about faulting, where if they use kind of realistic thermal structures, they have to include some weakening in the sort of transition into viscous behavior. Whether you've looked at how much of an effect if you have super weak faults or not terribly weak faults.
Very good question, and I don't know. No, I did not. I don't think we did that, Donna. No, we didn't.
No.
Sorry. It's really
Yeah,
good.
we talked about it a bit, but
Yeah, we did.
we don't have
Yeah,
results.
we did.
But you've been doing a lot, so
Yeah. No, that's a really good point. We started this out looking, as you said, at the core complexes. Like we were doing core complex models, and I think it was just that one of the 3 of us said we should do 40 kilometers, and we did 40 kilometers, and it sends you off on this kind of like, oh, that's cool. Mm-hmm. And there are so many other the fault weakening would be again another really good place to go.
Okay, thanks again, Donna and Megan. And we move on to the last talk.